Okay, let's break this down. You're walking along a path and your position depends on time. Let's call your position f of x, where x is time. Now, if you want to know how fast you're moving, you could look at how far you went over a short time. That's your average speed. So if you went from f of x to f of x plus h, your average speed is f of x plus h minus f of x, all divided by h. That's the change in position over the change in time. But that's just average speed. What if you want to know your speed at the exact moment x, not over a stretch of time, but right now? That's where derivatives come in. To get that, we shrink h. We make h smaller and smaller, like 0.1, 0.01, 0.0001, and we see what that average speed approaches. If it settles toward a number, that number is your instantaneous speed. That's the derivative. So the derivative is the limit of the average rate of change as the time interval goes to 0. It's like zooming in on your motion until you're looking at a single instant. Now let's look at this on a graph. Imagine a curve. Pick 2 points on it. Draw a straight line between them. That's called a secant line. Its slope is the average rate of change between those 2 points. Now move the second point closer to the first. The secant line starts to rotate and settle into a new position. When the 2 points merge, the secant becomes a tangent line. That tangent line just touches the curve at 1 point. Its slope is the derivative. So the derivative is the slope of the tangent line to the curve at a single point. Let's do a concrete example. Say f of x equals x squared. What's the derivative at x equals a? We use the definition. F prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. So f of a plus h is a plus h squared, which is a squared plus 2ah plus h squared. Subtract f of a, which is a squared, and you get 2ah plus h squared. Divide that by h, and you get 2a plus h. Now take the limit as h goes to 0, and you're left with 2a. So the derivative of x squared is 2x. That means at x equals 3, the slope is 6. At x equals -1, the slope is -2. That's how fast the function is changing at those points. So what does the derivative tell you? It tells you how fast something is changing. If the derivative is positive, the function is increasing. If it's negative, the function is decreasing. If it's 0, the function is flat at that point, maybe a peak or a valley. If the derivative is large, the slope is steep. If it's small, the slope is gentle. The derivative is also the best straight line approximation to the curve near that point. If you zoom in on a smooth curve, it starts to look like a straight line. That line is the tangent, and its slope is the derivative. Let's talk about units. If x is in seconds and f of x is in meters, then the derivative f prime of x is in meters per second. That's velocity. If f of x is velocity, then f prime of x is acceleration in meters per second squared. So derivatives aren't just abstract math, they describe real-world change. They show up in physics, economics, biology, and engineering. In physics, velocity is the derivative of position, acceleration is the derivative of velocity. In economics, marginal cost is the derivative of total cost. It tells you how much extra cost comes from producing one more unit. In biology, derivatives model growth rates, how fast a population is increasing or decreasing. In machine learning, derivatives are used to train models. Algorithms like gradient descent use derivatives to figure out which direction to adjust parameters to reduce error. The derivative tells the algorithm how to move to get better results. That's how neural networks learn. Now, let's go back to the graph. If you look at the graph of f of x equals x squared, the slope gets steeper as x increases. That's because the derivative, 2x, gets bigger. At x equals 0, the slope is 0. That's the bottom of the curve. As x becomes negative, the slope becomes negative. The curve is going down. So the derivative tells you the shape of the graph, where it's rising, falling, or flat. Here's another way to think about it. The derivative tells you how sensitive the output is to changes in the input. If you nudge x a little, how much does f of x change? That's the derivative. It's the slope, the rate, the speed, the best linear approximation, all in one. And it's a function, too. F prime of x gives you a new function that tells you the slope of f at every x. Let's try estimating something using a derivative. Say f of x equals square root of x. At x equals 4, the square root is 2. The derivative of square root of x is 1 over 2 times square root of x. So at x equals 4, the derivative is 1 over 4. That means near x equals 4, the function behaves like 2 plus 1/4 times x minus 4. So to estimate square root of 4.1, plug in x equals 4.1. You get 2 plus 1/4 times 0.1, which is 2.025. The actual square root of 4.1 is about 2.0249. That's really close. That's the power of local linear approximation. But derivatives don't always exist. If a function has a corner, like absolute value of x at x equals 0, the left and right slopes don't match, so there's no single tangent line. The derivative doesn't exist there. Same with cusps, jumps, or vertical tangents. Derivatives require smoothness. And finally, let's talk about notation. You'll see f prime of x written as f with an apostrophe. You'll also see dy over dx, which means the derivative of y with respect to x, or d over dx of f of x. They all mean the same thing, how fast f is changing as x changes. So to sum up, the derivative is the instantaneous rate of change. It's the slope of the tangent line. It's the best linear approximation to a curve at a point. It tells you how sensitive a function is to its input, and it shows up everywhere, in science, in engineering, in economics, in machine learning. It's one of the most powerful ideas in all of math.